Alright, so section 5.6, part 2. We're going to do a couple of examples here using the inverse trig function. So no new notes really, basically just going to go over a couple of examples here. So let's go ahead and get started. So we want to find the derivative of this, and basically what this is just a problem practicing simplifying. So it's one step of calculus doing the derivative and then a couple of steps of algebra to simplify it. So let's go ahead and do this one here. So to find the derivative, we got y prime equals, as we went over in the previous notes, the derivative for arc sine x. The derivative of x is 1, so 1 goes up top. And then the denominator is square root of 1 minus the inside, which is just x squared, so x squared. Plus, when we do the derivative of this second part here, this is a product rule because we have two functions. We have the function x and we have the function square root of 1 minus x squared. So what I'm going to do here is I will color code these. So I'll color code that x is my green function, and then the square root of 1 minus x squared is my red function. So when I do this derivative right here, we're going to do the derivative of the first, which is 1, times the second, so times square root of 1 minus x squared, all under your square root, plus, product rule here, the first, which is x, times the derivative of the second. So the derivative of the second, remember whenever you have a square root, the derivative of the inside goes on the top, so that's negative 2x, and the denominator is 2 times the square root, which in this case is square root of 1 minus x squared. Okay, so we're going to do a little simplifying here. I got these 2's that can cancel. Like I said, from here on out, this is all just algebra practice, reviewing, simplifying fractions. So y prime, I got 1 over square root of 1 minus x squared, and then I got a plus square root of 1 minus x squared. I'm going to leave a little space there for when I do my common denominator. Minus, so minus, I have x times x is x squared, over, and my denominator, again, square root of 1 minus x squared. Okay? So, again, I left a little gap here because I have to get this common denominator. So what that means is I need to multiply this by square root of 1 minus x squared over square root of 1 minus x squared. Right? I haven't changed the value of it. I multiply by something that is equal to 1. So this will help me to get a common denominator for everything, and I can simplify this, put it all in one fraction now. So y prime equals, I'm going to put a big fraction bar here. So I have 1 from this numerator plus, and then this numerator, when I multiply these, all it does is get rid of my square root and leave me with 1 minus x squared, and then minus this numerator is x squared. And this is all going to be over 1 minus x squared. Alright, so let's clean that up. 1 plus 1 is 2, minus x squared is 2x squared, all over square root of 1 minus x squared. And it might look like that is completely simplified, but if we go ahead and factor out a 2 from the numerator, I end up with 1 minus x squared. And then my denominator, I'm going to rewrite this one just so it looks a little better, like this. So this is a power of 1. The denominator is a power of 1/2. And from Algebra 1, we learned that if we have two things that have a similar base, in this case 1 minus x squared, we can subtract the exponents. So my final answer here is 2. When I subtract, 1 minus 1/2 is 1/2. So I have 1 minus x squared to the 1/2, which is the same thing as square root of 1 minus x squared. So that whole thing simplified to this. Okay, but again, one step of algebra, or I'm sorry, one step of calc right here, and then 1, 2, maybe 3, 4 steps of algebra in between. Alright, next problem. Find the horizontal asymptote. So we'll do these in two parts. The horizontal asymptote, that'll be my part A. And the critical number or numbers, there could be more than one. That'll be my part B. Of the graph of y equals arctan x, that whole quantity squared. So, horizontal asymptotes, part A. Now we learned in pre-calc and earlier this year that horizontal asymptotes, we had those three cases where we're dealing with the top of a fraction and the bottom of a fraction, and we looked at it that way. Arctan is not written as a fraction, so the other option, hopefully you remember this, the other option for looking at horizontal asymptotes is looking at the limit as x approaches either positive or negative infinity of this function, which in this case is y. I'm just going to write y. You could write arctan. I'll write it since I'm already doing it. Arctan squared. Okay, so let's look at, as we plug in infinite numbers, ratios, or negative ratios in here, what is happening to this angle? And this is where, if you covered the trig graphs, this would be very helpful. Or if you covered the inverse trig graph, that it makes it even easier. So the inverse trig function, well, first of all, the trig function, it looks like this. We have a bunch of things that kind of look like the x cubed graph, but not really. So the inverse trig function basically just takes all of these and flips them over, but really we just look at like this portion of it right here, and it just kind of looks like, oops, that was the wrong way. Let me back up. There we go. It kind of looks like this. So it's flat, and then it curves up, and then it's flat again that way. So the question is then, what is this horizontal asymptote? Okay. So, and again, if you covered that in pre-calc, then you already know. But if not, we come back up here. So the horizontal asymptotes here came from the vertical asymptotes up here. So where were the vertical asymptotes in tangent? What were the values for tangent that gave us undefines? And that is at the positive and negative pi over 2. We talked about that in the 561 notes, so hopefully you remember that also. So arctan, as we plug in infinitely big or infinitely small numbers, we will either get a positive or a negative pi over 2. And then we're squaring that, so we don't really need the positive or negative when we square it, because whether we square a positive or we square a negative, we're still going to get a positive. So this ends up being pi squared over 2 squared, which is 4. Okay, so this is your horizontal asymptote for that graph y equals arctan x squared. All right, part B asks us to find critical numbers. So we had two ways of finding critical numbers. We could do this either with the first derivative test or the second derivative test. Personally, I'm not a fan of the second derivative test, mainly because you have to do the first derivative anyway, so we might as well just do the first derivative test, which says take the derivative. Now, if we're starting, let me back up here, because I know I scrolled up and you can't see the top function. So this is the original function, tan x squared. So when we do the derivative, first of all, we have chain rule happening here. The outside function is squared, so we have 2 times arctan x, and then times the derivative of the inside, which is arctan x. So the derivative of that, as we covered in the previous day's notes, is 1 over 1 plus x squared. So if we want to see where this 2 arctan x over 1 plus x squared, if we want to see where that's equal to 0, we just set the numerator equal to 0. So the numerator, 2 arctan x equals 0, where does this happen? Well, you can divide the 2 over, if that helps you to see it any better, but hopefully you realize that arctan equals 0 when x equals 0. So there is only one critical value here, and that is when x is equal to 0. All right, next and last problem. So go ahead and pause the video and write that down. I will do my best to draw an accurate picture here, but may be kind of challenging with the tablet that I'm using. So we'll see how we do. Okay, so a photographer is taking a picture of a painting that is hanging on a wall in an art gallery. So let me first of all draw that part of it. So here we go. Here's the painting. We're looking at basically like looking down the side of a wall. So this is the wall. Over here is the wall, and then the bottom is the floor. So here's my picture hanging on the wall. Okay, that black mark there. It is 4 feet tall. Okay, so from here down to here, we know that's 4 feet. What else do we know here? The camera lens is 1 foot below the lower edge. So basically, if we look at here, we're going to say this will be like our 1 foot. Basically, this distance right here is 1 foot. So that is where the camera is. This is my camera. It's a great camera, I know. So there's my camera. So we know that from the information given, that is 1 foot below the bottom of the painting. Our question here is how far should the camera be? So what should the distance from the wall to the camera be in order to maximize the angle subtended by the camera lens? So maximize, there's your key word. That means this is an optimization problem, okay? So we have, I'm going to try and use different colors here. So we have that angle, and then we have this angle up here that I will draw with blue coming down to the camera like that. All right, so we have 3 angles here, okay? We have, first of all, big angle right here. This is the big angle. I'm going to call that theta. Then I have the green angle, which will be this part right here, which I'm going to call that alpha. And then I got the blue angle right here, which I'm going to call that beta. All right, so we know that that theta is the result when we add angles beta, and alpha together. Okay, typically for trig, when we're using angles for trig, we stick to the Greek alphabet, but you could use, I mean, we don't want to use X because that's what I have labeled on the bottom. You could use A, B, and C there if you wanted to. It doesn't really matter. Take your pick. Now, what we're asked here is how far should the angle of the camera be, or how far should the camera be away so that we have the maximum angle. Now, angles alpha and theta have right triangles that are being formed, okay? But angle beta does not. So what we're going to do then is rewrite this in terms of beta, because like I said, we know that theta and alpha can be written as right triangles, which we can use right triangle trig then. Okay, so beta is, if we subtract alpha over, beta is equal to theta minus alpha. So what do we know? First of all, we know that theta, if I'm looking at this big triangle here, we know 2 things. If we look at this in terms of arctan, remember arctan is opposite over adjacent, so opposite would be this whole piece, which is 4 plus 1, which gives you 5, over the bottom, which would be your adjacent, which is x. This is also the same thing if we look at arc cotangent, but the reciprocal would be what we're going to use for the angle. So it would be adjacent over opposite, so that would be x over 5. Now, it does not matter which of those you choose to use, but this option right here is easier because the derivative of the inside is easier to do. It would still give you the same answer if you use this one, but the derivative of 5 over x is harder to do than the derivative of x over 5. Okay, the derivative of x over 5 is just 1/5. But the derivative of 5 over x, that's negative 5 over x squared, which just is, it's harder to do that one. So I'm going to use the one that I have the red check mark by. Alpha, similarly, we have 2 options. We have arc tan of, in this case, the opposite would be 1 over the adjacent, which is x, which, again, we can use arc cotangent of the reciprocal of that, which is just x. And hopefully, again, you see that that is the easier one to use. So while you have some options here, one of your options is easier than the other. So I'm going to use the arc cotangents instead of the arc tangents. All right, so let's plug them in now. I have beta is equal to arc cotangent of x over 5 minus arc, let me put a little barrier here so we know this is a separate part, arc cotangent, whoa, sorry, let me erase that. Tablet kind of freaked out there for a second. So arc cotangent of just x. Now, since we're trying to do, let's go back to the problem and see what are we actually trying to do here now that we have it set up. Maximize means take the derivative and set it equal to 0. All right, so the derivative here, beta prime, or you could put dB dx if you wanted to. The derivative of arc cotangent, we put the derivative up top, so the derivative of x over 5 is just 1/5. And we also have a negative here because tangent is positive, but cotangent, arc cotangent is negative, okay? And then we have 1 plus this inside squared, so x squared over 25. Minus, again we have a negative, the derivative of x is 1 over 1 plus inside squared. The inside is just x. All right, and again, calculus is over, now algebra takes the place and finishes out the rest of the problem. So I don't like this. Fraction in a fraction, that's messy, so let's clean that up. So I'm going to multiply this by 25 over 25. Okay, I multiply by a fraction equal to 1, 25 over 25. So negative 1/5 times 25 is negative 5. And on the denominator, don't forget we have to multiply this through. We don't want to just multiply that fraction. So 25 times 1 is 25, plus 25 times x squared over 25 is just x squared, plus 1 over 1 plus x squared. Okay, all I did there was my double negative to clean that up. So common denominator means I'm going to take negative 5 multiplied by this, 1 plus x squared, plus 1 times this denominator, 25 plus x squared, and that is all over the whole thing then, 25 plus x squared times 1 plus x squared. Now, to optimize this, we want to take the numerator and set it equal to 0. I don't really care about the denominator. I just want to set the numerator equal to 0. So let's simplify this. Negative 5 minus 5x squared plus 25 plus x squared equals 0. So negative 5 plus 25 is 20. Negative 5x squared plus x squared is negative 4x squared. Where is that equal to 0? Well, 20 equals 4x squared. So x squared is equal to 5. Therefore, x is equal to, now we don't need the plus or minus because we're talking about a distance. So we're just going to have the positive square root of 5. Okay, if you plug that in your calculator, you get approximately 2.236 feet. The angle measure is about approximately 0.730 radians, but we don't need to know that. All we needed to know is approximately how far away from the painting did we need to make that camera so that we could, maximize the angle. And again, like I said, the angle, if you really care, was 0.730. I think it was 7.297, so it rounded up to that. Okay? So here's some problems, and again, if you have any questions, send me an email and let me know.